Everyone, my name is Pierriccardo Olivieri. I'm here to present our work made in collaboration with Mehrnoosh Askarpour and Elisabetta di Nitto about an experimental implementation of discrete time quantum walk using the IBM Qiskit library. Just a few words about us. Elisabetta di Nitto is a full professor at Politecnico di Milano. Mehrnoosh Askarpour is an adjoint assistant professor at McMaster University. And I am Pierriccardo Olivieri, still a master student of computer science and engineering at Politecnico di Milano. So the aim of this paper is to provide our implementation of two quantum walks model for a cyclic graph with 8 nodes, namely the coin quantum walk and the Zegadi quantum walk. For both of them, we extracted the circuit from literature. Then we provide an implementation using the IBM Qiskit library. And we run an experiment both in simulation and with the real IBM quantum computer, showing the results that we obtained. So random walks are a stochastic process that consists in successive summation of random and independent variables over a mathematical space. They exist in two types: discrete time if time belongs to natural set, or continuous if times belong to the real set. Here our focus is on discrete time. Below we can see a picture that is an example. We can see the line of the integer number, positive and negative, and we have our walker that is currently in position 0. Now what we want is to perform a random experiment that could be, for instance, a coin toss. And depending on the outcome of this random experiment, we want to move the walker on the left or on the right. We can achieve that by increasing the position or decreasing it by 1. What we obtain at the end is, by repeating these steps, we obtain a random path over this mathematical space. Quantum walks are the analogous of random walks. And again, our focus is on discrete time quantum walks. But in this case, each quantum walks define its components, as we will see in the next slides. So we can start with the first model, that is the coin quantum walk. On the right, we can see the cyclic graph with the labels of each node. And we can define the elements that compose the coin quantum walk. First, we have the position that is represented by vector of 3 qubits. We need 3 qubits in this case to encode our 8 nodes in a binary way. And the labels are here near the nodes. The coin in this case, so our random experiment, is a vector in a 2-dimensional Hilbert space defined by the cat0 and the cat1 here, HC. Then we have the shift operator that increase or decrease the actual position of the walker by 1. And the mathematical space in which the walker move is defined by the Kronecker product of the Hilbert space of the position and Hilbert space of the coin. Finally, we can represent the coin quantum walk operator as a single operator U defined by the shift and the coin operator. So this is the circuit that we implemented. Here we can see the last 3 qubits representing the position of the walker. The first qubit is for the coin. And here we can see these two sub-circuits, the Increment Circuit and the Decrement Circuit. They basically form the shift operator, and one increase the position and the other one decrease the position by 1. Only one of them can be activated, and we decide this by the outcome of our coin. This is the Hadamard gate coin. So we choose the Hadamard gate coin for its simplicity. We just have to apply an Hadamard gate. And in literature, we can find also different type of coins. Then we have our increment circuit This is composed by succession of controlled and multi-controlled gates. Its behavior is to increase the actual position by 1. And in the right, we can see code in Qiskit to implement it. It's very simple. We have a succession of controlled and multi-controlled gates. It is worth to mention the function MCT that is used to build controlled gates with more than 2 controls. Here we can see the argument of the function that are the controls, the target, and the mode, that in this case is no ancilla, and we will see later why this is important. Then we have the decrement circuit that is very similar to the increment circuit. They decrease the actual position by 1. And now we have negative controlled and multi-controlled gates that are basically obtained by negating the control before and after with the NOT gate. So this is the final decrement circuit. As we can see, also the code is very similar to the increment circuit. We just added the NOT gates. And this is the final circuit. The links for source code and the QX simulation can be found in our paper. And now we can discuss about the results that we obtained by performing 5 experiments. In the right, we can see a picture of an averaged picture of the results that we obtained. We used as a backend the IBM Q Athena. We choose this one because we need at least 4 qubits. And IBM Q Athena provide 5 qubits with the highest quantum volume given our account type. We choose to perform 1 step of the work. And here in the right, we can see the results that we obtained. In the x-axis, we have the labels that represents our nodes. In the y-axis, the probability to find the worker on a given node. And with the black bars, we can see the simulation results. Indeed, we have a 0.5 probability starting from the position 0 to move in node 1 or in node 7. White bars instead represent the real simulation on the IBM quantum computer. We expect to find the 2 highest probability in the correspondence of node 1 and 7. Here we have the highest probability on node 1, but unfortunately we have the second highest probability on node 3. So this is an outlier, and we assume that is due to noise. Also in node 7 we have the third highest probability, but still we have this outlier. Now, what about generalization of this model? Basically, we implemented a specific graph, a specific circuit for a cyclic graph with 8 nodes. And so we can ask how to scale with quantum walks. We can scale with respect to graph family, for instance. In literature, there are examples about circuit for torus and complete graphs. And to construct this, we need to alter the circuit accordingly. Or we can also scale with respect to graph size. Again, we have to alter the circuit accordingly, but in this case, this come also with a cost. Increase the size of the nodes means to increase also the multi-controlled Toffoli gates, and this means to increase also the resources, as we will see in the next slide. Here we can see how to build multi-controlled gates with more than 2 controls. In Qiskit, we used the function MCT, and here we report 2 approaches found in literature, just to show how complex is when we have to increase the number of nodes. Basically, we have here 2 approaches, the one of Nielsen and Chuang that uses ancillary qubits on the left. And here we use 4 ancillary qubits that are only used to construct the gate, to construct a 5-controlled gate. In the right, sorry, we can see instead the approach of Barenko et al. Now, this is an example with a tree-control multi-controlled gate. And as we can see here, this is a no-until approach, so we don't use more qubits, but we scale in depth. Both of these approaches needs more resources, so this is why it's for now it's problematic to construct a circuit with a lot of nodes. And now we can talk about the second model, the second circuit, that is the Zegadi quantum walk. Zegadi quantum walk is a quantization of a classical random walk of Markov chain. And now the walk occurs on the edge of a bipartite graph. Bipartite graph that is obtained by the initial cyclic graph with 8 nodes by duplicating the nodes in 2 sets and connect each node with its neighbor in the opposite set. We will see an image in the next slide. Now we just define the elements of the Zegadi quantum walks that are the state vector. It is our position composed by 2 vectors R1 and R2. Then we have the main operators of the Zegadi quantum walks, the swap operator and the reflection operator. We didn't report here for simplicity because they are kind of complex. So interested readers can find them on the paper. Our mathematical space now is defined by the canonical product of H1 and H2, respectively the Hilbert space of register R1 and R2 that are both of dimension 3. It is the number used to encode our nodes. And again, like for the quantum walk, we can express the one-step Zegadi quantum walk operator with U that is given by the swap operator and the reflection operator. Now, the graph representation is given by the adjacency matrix A. It is then used to build the transition matrix P that represent the transition probability of a node to its neighbors of the graph. Here in the right, we can see the bipartite graph obtained by duplicating the nodes and connect each node with its neighbors on the opposite set. And then we can define now the initial state of the walker that is given by a column of the transition matrix P. In this case, we represent phi0, that is the node 0. Indeed, we can see that we have an equal probability to move on node 1 and in node 7. This state is prepared on register R2 before the circuit. We can prepare it using another NOR gate and a controlled NOT gate. And the expected output is given in register R1. And in this case, we expect an equipobability of the adjacent nodes. This is our final circuit for the cyclic graph with 8 nodes. At the end, we can see our swap operator. Now, the first 3 qubits represent register R1. The last 3 qubits represents register R2. And this part of the circuit in the middle is the reflection operator. Again, the links of source code and the Kirk simulation can be found on the paper. And now we can talk about the results that we obtained with the Zegadi quantum walk. Again, we run 5 experiments. In the right, we can see the averaged results obtained. Now we used as the backend the IBM Q Melbourne 16. We choose this one because given our account type was the only backend with at least 6 qubits. It is the minimum requirements for our instance of the problem. And this backend provides 16 qubits and a quantum volume of 8. Again, we performed just one step on the IBM quantum computer. On the right, we have a similar structure of the previous experiment. We have on the x-axis the nodes, on the y-axis the probability to find the walker in a given node, and in black bars we have the simulation that in this case is again starting from the node 0, is again 0.5 to find the worker in position 1, or 0.5 to find the worker in position 7. But now, unfortunately, the results that we obtained for the real simulation doesn't match our expectation. We have a lot of outliers and the results are very bad. Assuming that our implementation is correct, we assume that is due to noise. So now to conclude this presentation, here we wanted to provide our implementation for these two QuantumWorks model and share the results that we obtained with the IBM quantum computer. But this is just this work is just a starting ground. Our initial idea was to build a library for a QuantumWorks model to wrap the complexity of build this circuit. And for now, we just use this work to experiment and to gain knowledge on this field and to understand the limitations, because at the moment we have important limitation both on the resources and on the noise in the current available quantum machine, at least for our experience. This, I want to end the presentation, and I thank you for your attention.
Thank you very much for your nice presentation. So now we have time for some questions. So first question is from Raikov. Yes, you are mute.
How easy is to generalize your graphs to any graph? Because your examples were either circle or bipartite or complete, or but not something totally generic.
Yeah, for the moment in literature, we found only simple examples of graphs. And I think that this is also due to the actual limitations. Just to run one step on a cyclic graph, that basically is really simple. It's a very simple graph. We had a lot of noise, we experienced a lot of noise. And so I think that now maybe we have this small implementation for specific graphs, and maybe in the future we can generalize with respect to bigger graph or generic graph, but this is just my hypothesis.
I'm asking this question because one recent trend in neural networks is to make convolutions on graphs of any type, not only sequential or grids. And maybe your work is some beginning of the something in the direction of some simulation of simple graph convolutional networks.
Yeah, the main objective was to build this library, also to prepare something for application in deep learning. I saw something in literature about application of QuantumWorks and deep learning, and yes, I hope to be able to continue this work and to provide something for bigger applications.
Thank you.
Thank you.
Yes, so we can take a few more questions if anyone has any discussion points.
How big are the applications that you can solve at this point?
At this point, given our account type that is the free account provided by IBM, we tried to solve this problem that is presented in the paper. So a cyclic graph with 8 nodes and just one step. So for now, the results are, the application are for very small graphs.
Mm-hmm.
And the noise is very high, and probably probably it's better to experiment with a more powerful quantum machine to understand the real limitations.
Right. Have you played simulated different levels of noise or not?
Yes, this is why we average the experiments, and we also have to try with different backends. But now this was we have a constraint because, for instance, as already mentioned in the presentation, for the Zegadi one, we just have at our disposal just one backend, and for the other approach, we have at our disposal more backends, but with less resources. So for the moment, we have a strong limitation that also in the noise that we perceive during the experiments.
Right. Thank you.
Thank you.